Just delete because you don't want it being
So, good morning everybody. So I'm going to continue describing the adjoint method, in particular showing the performance of research of the adjoint method, and I give additional information about the method itself, and in particular from the next lecture I'm going to describe the adjoint method for partial differential equation as such, not ubiquitous. There's no direct numerical implication, but still I think it's very well, it must now have been rather clear from what both Pavel and I have said so far, but the costly part of assimilation of meteorological and oceanographical assimilation may be different in other fields. But in the field we work in, the costly part is not really to have an estimate of the state of a system by itself. It's to have an estimate of the associated uncertainty, and more precisely, to carry that estimate in time, to determine how the uncertainty evolves in time. Well, Kalman filter does that explicitly by either by evolving a nearer covariance matrix in standard Kalman filter, as defined by Kalman in 1960, 50 years ago, or by evolving an ensemble of points in state space, an ensemble Kalman filter does that explicitly. Variational assimilation, as I described it, doesn't do that explicitly, but I'm going to show that it does enough of it for precisely because of the adjoint equation. It does enough of it to at least obtain an estimate, which, in the case when everything is Gaussian, is the same mathematically as the result produced by Kalman filter. So I remind you of what variational assimilation is. We have observations distributed over a period of time, typically in meteorological application 12 hours. We have a numerical model of the flow, which given a set of initial conditions computes on the computer with the history, the corresponding evolution of the flow to some degree of accuracy. And we want to determine, and in what I've said, which is called strong constraint variational assimilation. Strong constraint, I've not said this word yet, means that it is assumed that the numerical model is exact, that there is no error in the numerical model as a simulator of the flow. Then we look for the initial condition at the beginning of the assimilation window, such that the ensuing orbit fits best in the sense of a precise measure defined by the objective function, fits best the available observation. And in order to do that, we implement an iterative minimization procedure, each step of which requires explicit knowledge of the objective function with respect to the initial state, the unknown initial state, current estimation of initial state, and the iterative process little by little goes towards minimizing the initial condition. Is that clear? Question? So, yes, the difficult part is to describe the uncertainty of the evolution of a flow. And to visualize that a little, I'm going to show you work done a number of years ago by my former student François Boutier. And this is an analysis, that is the description, of the 500 hectopotential geopotential field for a particular date, 1st of December 1990, 0 degree. And what was described, so of 70 depression, which circulation, particular day, was in a sense not very intense, for instance, but doesn't seem to be very intense depression. There was a slight depression I mentioned yesterday, but there was also always a depression in the Aleutian area, in the day it was not very intense. Anyway, what François Desboutier did was, on a case, by just integrating one model a very large number of times, to describe evolution against certainty. So, just by doing a very large number, doing systematic, crude ensemble simulation. So it took an initial covariance matrix for an initial uncertainty. And this shows the corresponding, not very good, but it shows the corresponding correlation, geopotential, between one point here and other points. It is essentially, well, this is one row or one column in the covariance matrix. Since the covariance matrix is symmetric, it is either one row or one column. It is correlation. Yes, it is in correlation between geopotential uncertainty at this point and geopotential uncertainty at other points. And it shows it to be positive and actually isotropic. It's inaggregated, but it's a matter of protection. Experience is isotropic, the same in no direction. And then involve that with a model by just taking a large number of realization of uncertainty, and for each uncertainty, integrating the model. You have no resolution. It was a T21 model. It was on the previous slide. I remind you that the present operational model of the MWF has a T, but if you don't understand what T means, T 1300, I think, resolution. You may figure, I showed the figure. It gives you an idea of corresponding solution from 20 to 1300. So it was crude resolution, but it did that by running the model a large amount of time. And after 6 hours of evolution, that is when you obtain from the correlation of the uncertainty, the 6 hours of evolution. First of all, especially, the range of uncertainty has increased. And now, it's no more isotropic, but it's strongly elongated in the east-west direction. And in addition to the positive kernel, which represents the first one, represents the positive, negative kernels are appear on either side of the positive kernel. And when you went on, within 24 hours, and this is what you obtain after 24 hours. Now the spatial extent of the correlation is much larger. And it's delimited now in a northwest, southeast direction. And now there are two significant negative kernels from negative correlation on the other side. So this is how the uncertainty involves. And I wouldn't be surprised, and I think you will believe me easily, if I tell you that this special evolution, particular evolution, depends on the current state of the flow. From one day to the other, you will have a different evolution. And of course, it is evolution of the day, which has to be explained and introduced in the assimilation process. And this is what Kalman's filter is meant to do, by carrying either an explicit covariance matrix or an ensemble of points which are meant to sample that uncertainty. But not in the sense, the difficulty, at least, what is numerically costly in assimilation of meteorological or oceanographical observations. So, to tell you how assimilation does that, variational assimilation, capable in the sense to do that, I show now pictures which are relative to one particular situation which also is interesting, actually, the paper which was written by another one of my former students, Jean-Eric Tepo, who now is the head of a satellite section, satellite data section at Siemens Energy. And in this situation, you can trade the dates, but it's for the 15th of October of which year, 1989, I think. On Wednesday, a strong storm hit during the night England, southern England, Cornwall, and northern France, and did damage. Significant damage. Both countries. Not many casualties, of human sickness. And so this situation has been studied in the following years. Well, I think people will be interested in numerical prediction. In a sense, that particular storm, for as far as Western Europe is concerned, has been superseded by other storms which have taken place in the summer class in Spain, in particular one. There were two, which called Lothar and Martin, which hit France, other countries. One on the 26th of December 1999, the night following Christmas, and the other one the following day. And both did caused strong damage, and I said more about Lothar. Well, and these are the one at least in Europe as typical storms. Since other storms have occurred, and it seems that the number of Indian storms is increasing. Is that a consequence of global warming? It would be too early to say. Global warming, since higher latitudes warm more rapidly than lower latitudes, global warming should decrease the latitudinal temperature gradient, which should decrease the intensity of circulation, because if there is motion in the atmosphere, it's basically because there is a latitudinal gradient differential. But at the same time, because of warming, the water cycle, the intensity of the water cycle increases, and the amount of energy released by condensation of water, which is one very important component of the triggering of strong storms, increases. So it's not clear what the balance is. Anyway, that, for that particular situation, again, that scanned pictures is not very clear. This shows the analysis increments in a Freud bar corresponding to height observation at the 250 hectopascal pressure rate. So there are 4 panels. So again, you must take my word for it. This is level 1,000 hectopascal. This is level 800,000 hectopascal. This is level 500 hectopascal. This is level 250 hectopascal. And so this is a 3D bar. I said yesterday with 3D bar. And in this particular context, 3D bar means an assimilation system in which whenever new observations are introduced into the model, it is a sequential system of observation, very similar to Kalman filtering. The system evolves in time, and whenever new observations become available, the state XB, background XB predicted by the model, is updated with new observation according to the formula XA externalized equal XB plus gain matrix times the innovation. And in this 3D bar, the background error covariance matrix, denoted PB or V, depending, was assumed to be independent of the situation. So there is actually no, the uncertainty on the flow was not carried in time. It was at every new analysis time, and this occurred every 6 hours. Every 6 hours there was new analysis. Every 6 hours new set of observations. It was assumed that PB was the same. And that PB was built, as I've already explained in one of my previous lectures, on a geostrophic hypothesis. So that the height observation given at this point. We introduce height change, induced a height change in the fields, which is represented by the isocontour lines, and the wind change in the wind, which is represented by small arrows you must be hardly able to perceive, which correspond to the rotation in this sense. If H is positive, it is anti-cyclone circulation. And this pattern was fixed for any observation, any observation at this height. The pattern would be the same, whatever the current situation of the flow. And this propagated to the 500 hectopascal level and down. Well, at the accuracy of the figure, it's not even seen whether it actually propagated to lower level. But this feature was fixed once for all. No, there was no in the case evolution. And now this is the same thing. This is the impact of one individual height observation at the end of a 24-hour variational assimilation. So there was a 24-hour variational assimilation with only one observation, that particular height observation at the end of the period. And it was started at the beginning, time 0, 24-hour difference in distance, from background covariance error background error covariance matrix, which was also that geostrophic matrix, the same as before. But now there have been 24 hours of evolution of uncertainty, represented implicitly by the adjoint equation, which comes into the process. And now, this is the impact of an individual height observation. See, but it's totally different. Actually, on the height, it defines two kernels of height observation. Because the system, because it is a result of a temporal evolution and the dynamics of evolution, concludes, yes, there may be much more uncertainty in the height here and there, but in other places. As you have the impact of the wind, you know, it goes as far, 2/3 into the Atlantic Ocean. And the impact is still very strongly visible at 500 hectopascal, and down even to 1,000 hectopascal. And that pattern depends on the particular situation on that day. I don't mean it is better, it depends. Now, the correction made by individual observations on the fields depends on the current situation. Yes.
So this is the case where the adjoint equation actually goes back and changes the initial condition you started.
Yes, yes. This is at the end of a period. There are iterations over 24-hour period in that case. And this is the impact on the change. This is the change. 24 hours. Background. An orbit model solution is computed for background. Minimization is performed using one unique observation at that time. But what's a didactic example? A numerical test intended at explicitly determining what the impact of one observation is. Actually, the impact of one observation is what I call a representer. So that's the representer of associated with one height observation at level of 250 hectopascal, located somewhere here. And so minimization is done, which leads to another initial condition and to another model solution. And so what is represented here is the difference of what is represented in this figure, and the difference between these two at the end of the period. Taking account that only one observation, this observation, has been used in the process. So, the pattern of modification is very significantly different from the pattern that we result from that geostrophic standard, you know, good for everybody, background error covariance matrix. And that's a similar example, not for a geopotential height observation, but for a 1,000 hectopascal observation of wind, of the geo component of wind. At this point, now, at this point. So this implies a high correction which consists of two kernels, a negative one and a positive one, because of a gyroscopic approximation which underlies the definition of a covariance matrix.
That's 1,000 millibar high.
And height and width observation, which also has the kind of positive on one side, negative on one side, but we didn't state clearly in the figure. But I showed you schematic figure which describes the shape schematically, the pattern of it. And it extends to 500 hectopascal and slightly to algorithm. You see it. And now for that particular situation, the same thing, just another observation. You open that. In totally different structure. In particular, that individual observation at 1,000 hectopascal, define complicated structure and modification in the wind field which go almost all across the Atlantic. Yes.
Is the difference between the contours the same as well, so it's much stronger here as well, or is it a different scale?
No, it's much stronger. It's much stronger. It's not a different scale. Yeah. It's much stronger.
Wow.
And the correction propagates to the 250 millibar per Pascal level. Much stronger. And it's because the system, over a 24-hour period, the system is able to tell the uncertainty on the initial condition, described in that case by that raw, simple, almost simplistic covariance matrix, as evolved into that because of a particular dynamic execution of the flow. So the system corrects the fields according to what the system, to what it thinks the errors are. This is what it does. So there is obviously a very strong impact. There is obviously a very strong impact of on the correction made on the field by the fact that over the assimilation period, the system implicitly, because of use of the Android model, is implicitly knows something, or thinks knows something about a pattern of its sentence. Actually, if Kalman filter was implemented of execution, both what is shown here would be rows of P of predicted background error covariance matrix. The system by Kalman filter evolves, standard Kalman filter evolves covariance, the background error covariance matrix from a PA to PF, and that would be columns in the PF, predicted by the model. That's the variation of assimilation without explicitly computing this is able to be implicitly enough of it not to have an explicit description of the uncertainty at the end of the period, but to know enough of it so as to correct optimally the fields. Okay. So this shows that variation of assimilation has a strong impact. This doesn't show that the impact is positive in terms of qualitative result. That's another matter. But, well, actually clean comparison for this kind of thing are very difficult to make. ECMWF did make with comparison on how do we call it? Whenever they want to make a change in the system, they define the change, and then there is a period during which they run in parallel every day two forecasts, one without the intended change, and one with. And they look every day at the difference. So several situations may occur. It may see that after 3 days it's so obvious that the impact is negative that the modification is adopted without any further ado. Or it may soon appear that the impact is the fact of the change is so negative, but let's forget about it. Sometimes it might take us longer time. Typically this lasts a few weeks. And of course, they did that when they decided to go to 3D bar to 4D bar. actually, before, you can say that, before they did they started doing variational methods, they used the system which belongs to the general class of optimal interpolation, in which they had background error covariance matrix, but they did the assimilation locally in space. That is, they had divided the volume of the atmosphere into boxes. They had divided the volume of the atmosphere into boxes. And for each box, four-dimensional boxes, for each box they took the observation within the box, the observation within the neighboring boxes, I don't know how far they did, and they did the assimilation in the analysis in that box using both observations, kind of local, with the idea that observations that are located far away from the analysis point do not have an impact on the Big Bang. Incidentally, once, when I did that in ULF, I looked at the divergence and velocity field produced by the analysis. And on the chart, you saw the boxes, you saw, these are isolines, but isolines at angular points along the boundary between the boxes. And you saw the boxes on the chart, which of course was not a very pleasant feature. Anyway, when they shifted to 3D bar, that is, instead of doing that by boxes, they minimize the global objective function, still using the same covariance error matrix, so except for this feature, and maybe a few other features which were modified at the same time, I don't remember. It was fundamentally the same thing, but it did find an improvement. And that's attributed to the fact that now the Odengo observation that are located far away should not have a strong impact on the analysis. At least it had a kind of smoothing effect, which was favorable. But now I'm confused because at Gering-Ackenberg and our colleagues at the University of Maryland have developed what they call a local ensemble transform feature, LETJF, L for local, in which they do precisely that. So I thought that you must have troubles with your boxes. No, everything is perfectly all right. So I don't know where. No. So at one time, at this material, they found that not using boxes was an improvement, but then Gering-Ackenberg said it doesn't matter. Yes, Pavel, you want to comment?
No, they don't have boxes, because they have box, yes. but they calculate analysis only for central point.
Yes.
In the box. For
yes.
central point in the box.
Yes.
And for the next grid point, they shift the box.
Yes.
So
but still it's local.
No, they don't see the box boundaries. Because the
shift is continuous. You mean the shift within the box?
Yes.
Okay, the shift point-wise. So you don't see, okay. So you cannot see the boundaries between the boxes because the shift is continuous.
Yes.
Okay. Maybe that explains maybe. Anyway, when we went to 3D bar, and then when we went to 4D bar, and with this time it changed from 3D bar to 4D bar, they made this comparison, and they found that there was a small but significant improvement of the assimilation in the analysis, in the quality of the forecast. Of course, the ultimate test is in the quality of the forecast. Actually, I was speaking a few minutes ago of a storm Lofin, which hit France on the morning of the 26th of December 1999. Actually, it was a Sunday morning, early morning, the day after Christmas. Very few people were out at that time. Still something like 70 people were killed in France. If that storm happened on a weekday at 9:30 or 10 in the morning, there would have been thousands, not 10,000 casualties. Although storm was quite predicted. And interestingly enough, it happened that at that time, at Météo France, it seemed the value have shifted to 40 bar in the fall of 1997, so that was 2 years later. And Météo France was precisely in the phase where it ran operationally both 20 bar and 40 bar in order to assess the impact of 40 bar. And the storm was predicted by both systems, but more accurately by 40 bar. But it was for a reason which is not fundamental. It was because in now millions of observations which are available every day, there is a proportion, a few percent of observations which are erroneous. Of course, it is highly desirable to filter out these observations. So there are tests, checks, so if an observation is well outside the physical range, possible physical range of particular factor condition is discarded. But the only thing that is used is to compare, look at the innovation, and the difference between the observation and the background. And to decide that if that observation, the difference is larger than the given threshold, then the observation is discarded. Of course, that can be very dangerous because there is typically a choice of if you make a mistake, there is no safe side. Either you correct, you reject an observation which is correct, which is far above the background, and it is all the more necessary and useful to use it because precisely it is very far from the background. Or you accept an observation that is erroneous, but may cause damage too. And in that case, it turned out that there was a threshold for rejecting observations, and that the phase of deepening of the depression of Lothar, there were observations which showed there was a deepening, but so were rather different from the background. But the 40 bar background, 40 bar had been running for it, was slightly more accurate than the 40 bar background. And this means that this unusual observation fell on the other side of the critical threshold, so that 40 bar rejected this observation which was for the background correct, while 40 bar accepted them. So 40 bar did produce a much better forecast. But because of the threshold effect, a small difference in the quality of the background was amplified by either rejection or acceptance of both observations. And this is another example. It may not be very spectacular, but it is typical kind of results you obtain when comparing 3D bar and 4D bar. So this is the situation of 3D forecast. Here for a 3D bar analysis, which produces two depressions on either side of ISO. And the forecast were about the same depth. And 4D bar produces a much deeper depression to the east of ISO and to the west. That's the real difference. Then you have to compare with reality. Well, reality is really a problem because we don't know reality by definition. If such simulation exists, it's precisely because we never know reality, even afterwards. So you have to compare each system with its own analysis. And the analysis is not the same depending on whether you use 3D bar and 4D bar. But whether it is 3D bar or 4D bar, the observed position of depression is much deeper on the east than on the west. So this shows that in this particular case, even 3D bar says that. So this shows that in this particular case, that forecast was more accurate. And this, typically, what it does not. When this kind of comparison is made, there is not a significant difference every day. Every now and then, every few days, at least somewhere in the atmosphere, there is a significant difference between 3D bar and 4D bar. And generally speaking, that's not always, 95% of the cases, the difference is to the advantage of 4D. Because precisely 4D bar is capable implicitly through the use of the algebraic equation of evolving, not explicitly evolving uncertainty, but to know enough, to implicitly know, determine enough on the evolution of uncertainty to be able to make an optimal correction. At this point, I said something. Question which is different. What do you do at the beginning of each new assimilation window? I have here assimilation window. Now estimate WF is using a 12-hour assimilation window. So at the beginning of a 12-hour, the background is defined together with covariance matrix of the associated error. What do we do? Well, so far, in the operational system, unless it doesn't, they still use a standard geostrophic covariant matrix, which is recycled at every new assimilation period. They are in the process of developing ensemble variation of assimilation, the output of which will not be one model solution, but an ensemble model solution. So that will produce not one model solution over the assimilation period, but a number of model solutions. And then this will produce an ensemble of possible states at the beginning of the next assimilation window, which will then define an uncertainty which is situation dependent. So I don't know which I know, this is what they are doing now. But it is true that for Divan, as it still exists at present, maybe not anymore at the Belgium, but in our process, still every assimilation window, we start with, I would say, the cold start for concerning the background error covariance matrix. It starts like that. Okay, questions on all that?
I have a question and a comment. First, a question. I'm still confused as to how the background error covariance matrix evolves over the 4D bar window. That it starts with like a climatological B matrix, but then after 12 hours, how does that evolve?
Well, it has evolved because in the adjoint equation somewhere there appears the Jacobian of the model equation.
Yes, you showed that yesterday.
Yeah,
so
so
essentially the Jacobian is just, it's
Well,
explicitly
It's
computed.
worth coming back to so that this is this was free. I've made this operator more visible. So in light green yesterday, I do not know that makes it so in white and I've put them in darker. Here, that's the model. Cycle Rodon at MK cycle, nonlinear. MK prime is the Jacobian. So this is the evolution, we describe the evolution of a small perturbation. If you put a small perturbation psi k, the corresponding perturbation of psi k plus 1 will be nk prime, not transpose, nk prime times the perturbation in psi k, the first order. So this describes, to some degree of accuracy, the temporal evolution of the error of the uncertainty. And it appears here in the implicit in the atomic equation through its transpose, but it is there. And it's why it is there, but the system, knowing how the solution emanating from size 0, from the current x 0, fits or doesn't fit, knowing accurately the solution emanating from size 0 fits the observation, but the system is capable, and knowing the fact that the model, the small perturbation in a small error evolves according to MK prime, and then you cannot decide to use MK prime transpose, which of course it contains the same information. It's capable to tell you must correct the initial condition in a way in this direction, because this is what will help you, taking account everything, in particular MK prime. This tells you how you must do the initial condition. So it is in that way that it implicitly, variational assimilation, implicitly knows about the evolution of the uncertainty, and is capable not, contrary to what Kalman filter does, to produce an explicit estimate of the uncertainty in occurrence, but at a higher cost, but to define the optimal correction. Yes.
A comment on what he said. I mean, the Hessian also can be used as a measure of the absorption. The Hessian.
The Hessian? The Hessian of what? Of the objective functions?
Yeah.
Yes. First of all, we don't have access to the Hessian.
Yeah, okay.
Gigantic. Yes, but the Hessian, of course, actually, yes, of course, you're right. The Hessian of J at the minimum, in case, is the inverse of analysis error covariance matrix. The matrix of second derivative of J at the minimum is the inverse of PA. So if we could have access to an explicit estimate of the Hessian of J, yes, we would have that same thing as the Kalman filter produced by another one. Other questions than that?
Yeah, I'll just make a comment on 3D bar versus 4D bar.
Excuse me, who?
So yeah, sorry. That probably people here have heard of scatterometer data from satellites, and so there was a scatterometer called QuickScat that was launched by NASA in 1999, and all the operational weather prediction centers became very reliant on this satellite, that it was just up there as an sort of more as an experiment, but then through the 2000s, the operational centers started to grow more reliant on these surface winds that were there on the oceans all around the globe. And then it came to 2007, and the satellite was getting old, and the former director of the National Hurricane Center said, well, there's no replacement that's being planned for the satellite, and these winds close to hurricanes can be very important for improving forecasts of hurricanes. Now, he based it on 3D VAR, and he said it completely wrongly, and it was partly a reason that he got fired later that year. And this all went to Congress, and there was a testimony on this, and it was shown, well, NCEP did a study basically with 3D VAR, the Navy had a published study, and they showed that there was just very little influence of assimilating these QuickScat observations on the tropical cyclone tracks. And I sort of followed up with it and found that, yeah, there's no influence, and it's because the influence only projects from the surface up to about 1 kilometre, whereas the cyclones really get steered like between a height of 1 kilometre and about 9 kilometres. Now, no one mentioned 4D VAR, that everyone just looked at the US models. If some of those increments, like you showed from, I think it was Boutier et al., 1993, that if some increments were showed from 4D VAR and some of those studies got done, it may have shown some very different results, that the surface winds could have had a real impact on the structure of the tropical cyclone and therefore the tracks. And there might be a replacement for QuickScat now.
Okay. Well, there are spectrometric observations going on. In fact, I did not show them in my first lecture, but I could have shown map of spectrometric observations.
Right.
And they are
The key is the vertical influence is just so weak in 3D VAR because there's no temporal evolution of that influence through the window. It's just a static influence in the lower level.
But does it mean the American Congress knows, at least heard about 3D VAR and 4D VAR at that time?
Well, a little bit, yeah. They didn't mention the words 3D VAR and 4D VAR, but
could be interesting how many others still remember that.
A lot of them got voted out since 2007.
Okay. Yes, and how much time? Well, I'll come back to that later. I'm going to describe now how more precisely one claimants we are driving. So he said the code must be written in the table, which that, in a sense, that's the costly part of variational explanation. Just developing, validating, and then maintaining the joint code in parallel with the business. Actually, in practice, it becomes very simple. I consider the code, that is the sequence, finding sequence, and arithmetic operation. So, for instance, on 3 input variables, not 3, one number of input variables, and then we copy and paste. It computes x1, x2, and x3. It computes an objective function, output function, the function, the gradient of which I want to know, j equals x1 squared plus x2 squared plus x4 squared. And x1 and x2 and x3 are combined functions of input, and j is the combined function of input, and I want to obtain an explicit expression, not an explicit expression, an explicit numerical value, an explicit estimate, not an explicit algebraic expression, but an explicit numerical estimate of the partial derivative of j with respect to the unit input. So, basically, just take the partial derivatives of j with respect to the current variable, and then proceed backwards. So, the partial derivative of j with respect to x1 is 2x1, 2x2 plus 1. And I proceed backwards. And I reach a state when, for instance, I have the operation somewhere in my code, A equals B times C. Simple multiplication. And this I consider as an operator, which has input, obviously input BC, and output A. Actually, it has also output BC, because B and C are still exist after I made this operation. And maybe it's used later in the code, I don't know. So I must take into account, when I look locally at this statement, at the coding statement, that this is an operator which has input B and C, and output A, B, and C. And so in order for clarity, I write that pretend that this is this statement, replace it by A equals B and C, B prime equals B, C prime equals C. Of course, I want to do that on the computer. And this has very special relation to C, because we prime independently of B. I won't do that. But I must do that for fully realizing what I'm doing. And since I proceed backwards, the partial derivative dg over dA, dg over d prime, dg over dc prime are available from the backward, from the adjoint computation which proceed backwards. And we want to determine dg over dB, dg over dc, who have the partial derivative with respect to the output, and we want the partial derivative with respect to the input. Okay. So I use the general dg over dd with respect to the input dBd is equal to dg with respect to the output A times dA over dB. d over dB, well, dc. Plus dg with respect to the output dB prime times the derivative dB prime with respect to dB. That's one. That plus dg over dc prime, dc prime over dB. That's 0. So the question, so dg over dB equals dg over dA times C plus dg over d prime. same thing for DGO, you see. So we have two coding functions of the adjoint which correspond to that coding function. And I do it systematically. Totally mechanical. But the first time you do that, it's fun. It becomes very tedious after a number of times. But that's all. That's all. And of course, when you use simple notation, instead of using typically what I will do is use, for instance, the same name for all that. So for A, I use A, I use B and C, including, for instance, in the adjoint codes. And this becomes B, for instance, equals B plus A times C. No, I don't care about having a B, a B prime, and having a partial derivative. Or if I'm confused by that, I write adjoint B, if I want adjoint B, equal adjoint B plus adjoint A times C. C is not an adjoint variable. It comes from the original code. And the fact that I'm using C at this stage, which I must have saved from the direct integration, or which I must be able to recompute at this stage, corresponds to the general fact that whenever there is a nonlinear operation in the sequence of expressions, then the parameter of that operation, the partial derivatives of nonlinear operation, depend exclusively on the value of the variables. So the value of the variable I must use again in the adjoint integration. That's why I use the C which comes from a direct integration at this stage. And same for that, adjoint C equal adjoint C plus adjoint A times B. So B is the partial derivative of A with respect to C. And that's it. Very systematic, very mechanical. And you see that here I have one multiplication here, and here I have two additions and two multiplications. For each 4 operations for the integration against 1 in the direct integration. That's the maximum. It's never more than 4. If everything is kept in the okay, of course, there are software pieces which do that. But still, they are not fully efficient. Although these software pieces are not fundamentally different from what standard compilers, Fortran compilers, are basically they have the same nature, the transform sequence of instruction into another sequence of instruction. But still, probably because we are less demand for adjoint compiler and for ordinary Fortran whatever compiler, they are not as efficient as compilers. This, I mentioned, requires plain writing of a direct code. In particular, we proceed backwards along the direct code. When we proceed backward in the direct code, we must be able at every stage to find out where you're going to come from. Let us suppose you have somewhere in the sequence of the and then something, what usually it says something, expression 50 go to instruction 100, and then the sequence of expression, and proceed backward here for the adjoint integration, and get here. Yeah. What did I do? How did I get to it? So it is necessary to have a direct code which is clearly written so that at every stage you can very well identify what input variables are and output variables are, and also to proceed backward in the linear code. Anyway, that's plain coding anyway. In order to be able to derive the adjoint of the code, it is preferred in the code that's written directly. Actually, what is most efficient is to derive the adjoint at the same time when you derive the direct code. It's It's a minor additional rule. If you do both at the same time, writing the adjoint 10% more. I first observe that there are shortcuts. If somewhere in the computation you have an operation which you know is a linear operation, but it can be represented by a matrix, then the adjoint code will be multiplication by the corresponding transpose matrix. In for instance, at one stage, you invert the Laplacian, you solve the Poisson equation, you invert the Laplacian. Laplacian is represented by a symmetric matrix. So the adjoint of the Poisson equation solver is the Poisson equation solver. You don't have to rewrite an adjoint code. Just take the same. The adjoint is the same because the Poisson solver is a multiplication by symmetric matrix. Another case which I say is the archetypal case is Fourier transform. F. Fourier transform verifies possible equality, which identifies a field X. And I take it by Fourier transform. The L2 norm for Fourier transform is equal to the norm of X. That's in spectral space, that is in physical space. That's true. So the general definition of a joint operator, I didn't cite the general definition of a joint operator is AX scalar product Y equals X scalar product A transpose Y. I'm an adjoint. Infinite. What the general definition of a joint operator? And if you take orthogonal coordinates, then the matrix which represents A star is the transpose, and so immediately by developing the scalar. This says that X times F adjoint F X equals X. And this is valid for NAX, which results that F adjoint F equals the identity. But the adjoint of the Fourier transform is the inverse Fourier transform. And the inverse Fourier transform is basically the same thing as the Fourier transform. It maybe has to the coefficient of pi rather than that. In any way, Fourier transform code, the Fourier transform always come with the inverse. So if you have the Fourier transform in your code and you want it to be adjoint, you don't have to write the adjoint of the Fourier transform. That's really what that really makes sense. One of the most absurd things to do in scientific coding, to write the adjoint of the Fourier transform. It's in here. So there are shortcuts. Okay, so